Everyone, today we are starting chapter 6. Chapter 6 is going to be a short chapter, so we won't do a full test in chapter 6. We'll just do we won't even have time for a quiz. It'll just be a big quiz little test that we have together. So it'll be super quick compared to kind of the longer chapters that we've been doing. We're still going to be working with probability, but chapter 6 starts to think about variables that are discrete versus continuous. So for today's lesson, we're going to ask the question, how many children are in your family? And if I was here in class, I would make sure that I would have you count up everything, but I'm going to actually just use the data from last year that I have since I'm not there today. So first thing I want you to be aware of is that in chapter 6, it does say let x equal the number of children. So we are going to have variables in this chapter. And so the variables are either a capital X or a capital Y, maybe a capital Z. I guess you could make them anything, except I probably wouldn't make it a capital P because then you'd think people would think it's probability. So if we were trying to have X be the number of children and we wanted to choose someone from the class at random, last year, oh my gosh, my numbers last year were so much smaller than they are now. Last year, I only had 1 out of 24 students say that they were an only child. I had 14 out of 24 say that they had a sibling. 5 out of 24 said that there were 3. 3 out of 24 said there was 4. 1 out of 24 said there was 5, and 0 out of 24 said that there was 6 or more. So that's 15, 20, 24. Yeah. So we're going to use this data here today just to help us with what we're trying to do, since I'm not there to count up your actual siblings. All right, so rewriting this, I'm going to leave them just as fractions for right now, but obviously we can change them to decimals if you wanted to. 1 out of 24. A little bit of review from last chapter. The reason that you know this is a valid probability model is 2 different reasons. So you should know that this is a valid probability model because why is my pen not working? There we go. Maybe, because all of the probabilities are a decimal between 0 and, oh my goodness, why is this not working today? 5, between 0 and 1, and all the probabilities add up to be 1. So 3 out of 24, 1 out of 24, there we go, and 0 out of 24. Now it's working. So you should be able to say that yes, this is a valid probability model because of the 2 things we talked about last chapter. The first one being that all probabilities are between 0 and 1, and all of them add up to 1. Now we're going to start to talk about discrete versus continuous, and this is where it kind of depends on the variable and what we're talking about. But since our variable x stood for the number of children, if a question was asking is 5.7176 a possible value for x, hopefully you would be able to say no, and that's because we're talking about the number of siblings, which means you can't have 0.7167 of a sibling. And in stats, we don't really care about oh, well, what if someone's pregnant? No, we don't worry about that. If they're here actually physically in the world, then they count in this situation here. So you would want to say no because this variable here is considered a discrete variable versus a variable that's continuous. A continuous variable would be something like height or weather or time, something that can be like decimals or values that are in between, versus discrete has to be set whole numbers. Super easy to make a histogram, so a little bit of review here, but it should be pretty easy to make a histogram. Just make sure that you read directions in this case. Generally, whatever your variable is, so x, that's going to be on the horizontal axis, and then your probability is going to be on the y-axis. It's going to be pretty ugly for me to try and do this, but I'm going to do my best. And then we'll describe the shape using our socks. So always make sure you're reading all parts of the directions and answering all parts of the questions. So once we're done, we then want to describe the shape. And we won't do all of the socks, it just says shape, so we'll just do shape. But if it did just say describe the distribution, then you would have to do everything. All right, so I am not drawing this to scale, so please be aware of that. This would be, we'll go 2, 4, let's see here, 2, 4, 6, 8, 10, 12, almost made it all the way to 14, I think. Maybe 2, 4, 6, 8, 10, 12, 14 along there. And then we'll have number of children. So 1, 2, 3, 4, 5, 6. So I have number of children, or in the house, children. And then this is going to be on the side, would be the probability would be up here. Probability, and I'm going to say my probability is in values of 1 out of 24. So that way I'm scaling it correctly. And then I'm just going to go ahead and draw boxes. So there was only 1 that had 1. There were 14 that had 2. There were 5 that had 3. There were 3 that had 4. Trying to keep the boxes as equally equivalent in shape and all that. And then there was 1 that said 5. So I could say like 1, 14, 5, 3, 1. There we go. And then if I were going to write or describe the shape here, I would probably say that it is slightly skewed right with a single peak at 2 children. Right, now we're going to kind of connect what we did last chapter with probability, and then we're going to make sure that we are kind of answering or looking at different notation, even though it's answering the same things. So describe in words what this means right here. Remember, this is proper probability notation, which you hopefully used on your test. So this is the probability that x is greater than or equal to 3. If I'm trying to actually specify it for this problem here, I would say that it is the probability that a randomly chosen student has 3 or more children in their family. That is everything that the AP exam would want to see if you were trying to describe what that means. The probability that a randomly chosen student has 3 or more children in their family. If I am trying to actually find the probability, x is greater than or equal to 3, I would then just go back to my my table there, and I would just add all of the fractions that are 3 or more. So 5 plus 3 plus 1 plus 0, which should be 9, which is 0.375. So the probability that a randomly chosen student has 3 or more children based in their family based off of my data from last year would be 0.375. If I was doing the probability of x is just greater than, and there's no greater than or equal to, essentially that is asking the exact same thing as above, except we're just looking for specifically more than 3, not 3 or more. This would just be more than 3. So it would still be the probability that a randomly chosen student has more than 3 children in their family. So you want to make sure we're not using inclusive language for the 3 because there's no or equal to. And this would be the exact same type of math, except you would not include the 5 out of 24 because I just want it to be the greater than. I am also going to continue to include the 0 out of 24, even though I know we technically don't have to write that. I do want to see some work. I don't want to just see 24 out of 4, because then I'll be like, where did you get that 24 out of 4? And I know that 24 out of 4 can reduce down to just be a fraction here, but we're going to have it go like this. And we're not going to put the repeating symbol. We're just going to round it to 6, 7. So the probability that a randomly chosen student has more than 3 children in their family is 0.1667. And I'm going to leave things as decimals unless it asks me to interpret the probability, or if it asks me to write it as a percent, I guess. That would be the only reason. Right, last thing here, if I'm looking at this problem here, find the average of the x values. So whenever you see in the word average in any sort of math, I would hope that we know that we're trying to find the mean. But what I want you to be aware of is that I don't want you to solve the average by just like adding the amount of siblings together. So if you were to just say 1 plus 2 plus 3 plus 4 plus 5 plus 6 and divide that by 6, and that gives you 3.5. That is technically incorrect when we are trying to find the average of the x values. And that's because we need to factor in the probability of each of those siblings because they don't all have the same probabilities. So what we're going to do is, using proper notation, I'm going to use mu sub x, which means the mean of the variable x, equals, I'm going to have all of the siblings, so I can have 1 sibling, 2 siblings, 3, 4, 5, 6 siblings, and then I'm going to multiply each of those by their fraction or their probability. So 1 out of 24, 14 out of 24, maybe 14 out of 24, 5 out of 24, 3 out of 24, 1 out of 24, and then I guess 0 out of 24, which is just 0. And then we're going to add all of those together. So when you take your time and you add all of those together, we should get mu sub x equals 61 over 24, which is actually 2.517. So technically the average, because we have to factor in those probabilities, the average is not going to be 3.5 siblings. The average based off of this class data is 2.5 siblings, which should make sense if you go back to our skewed data with the peak being at 2 siblings. That should make more sense. Okay. Does this value tell us the average number of children in the families of students in this class? If yes, explain yes. If no, why not? You would hopefully say, based off of what we just did, yes, because. But what I really want you to be aware of are 2 vocab words here that I want you to be aware of. In statistics, the first thing is that sometimes now, instead of saying the word average, the AP exam is going to say the expected value. So instead of saying find the average of the x values, it would say what is the expected value for this variable here. And so you would do this formula that we just did above. We do technically get this formula on the AP exam for how to find the expected value, but it looks like mu sub x equals, and then it looks like a big E sub x, or E of x equals, and then it's summation notation. So sum of xi times, times the probability of xi. And pretty much all that means is that, or all of those notational pieces just mean this is the mean or the expected value. I'll always want you to do mu sub x. You don't have to put the e of x. And then it is the sum of all the x values times their probability. And sum just means that you're going to add them all together. If you want to go to my OneNote to be able to see that formula sheet there, then you totally can. But I'll just show you on Thursday when I get there. But pretty much you should be able to, for today, go ahead and work on, you can leave the big box blank, but you should hopefully be able to do the problems that I have, the check understandings. They really shouldn't take too long. You should be able to just use the probability models given, and then either graph if you need to graph, describe shapes, and then find the expected value. Obviously, you can use a calculator. Let me know if you have any questions. You can technically find the expected value using your calculator with list 1 and list 2, but I'll have to show you that. You could probably figure it out, some of you. But I'll show you that when I get back tomorrow. So see you Thursday. Message me if you have any questions. Bye.